We'll discuss some of the physical applications of integrals, and we're going to look at two in particular: density and mass, along with force and work. And we'll start by trying to find the mass of a one-dimensional object. And this is going to be given by the integral from a to b of rho of x dx, where rho of x is our density function. And this will determine the mass. If we integrate the density, we get the mass. For our first example, we're going to try to find the mass of a thin 4 centimeter rod with density function given by 5 e to the minus x. This means we need to integrate from 0 to 4, which comes from the length of the rod. And we need to integrate the density function. When we integrate, we get negative 5 e to the minus x between 0 and 4. This means we have negative 5 e to the negative 4 plus 5 e to the 0, which is 5 minus 5 e to the minus 4 grams. We'll now consider something a little more complicated. This time I have a cylindrical tube. The radius of my tube is r, and the height of my tube is h. And this time we don't have a function of the density, but we have a function that gives our concentration in terms of depth. So we want to integrate this from 0 to h this time. We don't know exactly how tall this tube is, but we can integrate from 0 to h. We need to integrate density. However, you'll notice this concentration function is in grams per centimeter cubed. If I multiply by the area, which would be in centimeters squared, I would then get grams per centimeter, which is what I need. So we just need to multiply by the area. If I look at any given cross section, it is a circle, and the area of a circle is 2 pi r times our function c. I can pull constants out to make this a little bit easier to actually integrate. That then gives me 2 pi r times 0.2x plus 0.4x squared between 0 and h. If I stick in h, I have 2 pi r times 0.2h plus 0.4h squared, and if I stick in 0, I get 0. So now I have a function. If you give me a value for r and h, we can actually find the mass at a given point. We'll now look at another application that involves force and work. And this is very similar to our density and mass. We find work by integrating from a to b of our force. And the example we'll look at in particular is going to involve Hooke's law. And Hooke's law involves springs. And if we want to move a spring from its equilibrium point to a certain point, then the amount of force that's involved is equal to k times x, where this k depends on our stiffness of our spring. We'll start by having a spring that requires 20 newtons of force to stretch it 0.1 meters. So if we need to find our force, we have 20, and this is k times x, where x is the distance that we moved it, which is 0.1. Therefore, I have that my spring constant is k, or is 200. We now want to see how much work would take to stretch this spring 0.25 meters. So I'm going to be integrating from 0 to 0.25 of my force, which we found to be 200x dx. This means we have 100x squared between 0 and 0.25. And sticking this in, we get that this would take 6.25 joules of force. We're going to change this slightly and see how much work it would take to stretch it 0.25 meters if we started at 0.1 rather than the equilibrium. Therefore, my lower bound is going to be 0.1 since that's my starting point. Since I'm stretching it 0.25 from here, my upper bound is going to be 0.35. That way we actually do move a total of 0.25 meters. And then we had our force function of 200x. This is now 100x squared between 0.1 and 0.35. That gives me 100 times 0.35 squared minus 100 times 0.1 squared. If I start with the first one, 0.35 squared times 100 is 12.25. The second one, 0.1 squared times 100 is 1. So this would take 11.25 joules. Even though we're stretching at the same distance, we're actually having to move to a further point away from equilibrium, which takes more work.